Okay. Well, good afternoon, everybody. Today we are doing the second to last part of the course. We have one more class left. And the subject for today, as well as the next class, are going to be the relativistic description of electrodynamics. So we first looked at the relativistic electricity and magnetism on Monday, and we introduced this this physical source object that was the four currents that had in it the charge density as well as the current, and then we also wrote down the wave equation for the vector potential and for the scalar potential. And we show that in the Lorentz gauge, that means that there's a natural choice for then afterwards picking a generalization to the potential, which we call the forward potential, which had just as the temporal part just the scalar potential, and as the spatial part the vector potential. Now we did that, and then we're able to kind of put things together, but we haven't. Oh yeah, and then of course, you know, I showed you how doing that simple Lorentz transform, you can actually explain why the cross product works when you have the classic Lorentz force. You know, there's this QV cross B, and now hopefully you can understand why that comes about. So a couple of notes about that. So I made I did that calculation in a manner that was most easy to see. So it's most easy to see that if you have a neutral wire that is a current carrying wire, and that generates a magnetic field, and therefore in the frame where that charged object is moving, there's a magnetic Lorentz force. And that's the only force that you have, right? Because the wire is neutral. So then when you do your Lorentz transform, then all of a sudden your wire is charged, and in the co-moving frame, your charged object is not moving, so therefore the magnetic part of your Lorentz force is zero. And now that means that you've gone from a purely magnetic origin of the force to a purely electric origin of the force. And that's the easiest way to see how that conversion comes about. But it's not strictly necessary. For instance, you could start with a current carrying wire that is just a beam of charged particle, right? So you have, you know, at CERN and places like that, and some of the undergraduate physics labs, we will have beams of charged particles, and those obviously would also generate a magnetic field. It's just that it's already a charged object, so then you have two contributions to the force, and it's not immediately clear from a pedagogical point of view how that magnetic contribution comes about. So that's why I started with a neutral wire, because it just is easiest to see what's happening. But rest assured that that's still that description is still correct. It's just becomes a little bit more hairy. Okay, now so we had in the Lorentz gauge, we had this straightforward connection between the potentials and the currents, and it's just a D'Alembertian acting on that four potential gave you the four current. And as usual in electricity and magnetism, all of the problems that you want to that you want to solve usually involve something like, okay, I have some kind of charge distribution or some kind of a current distribution, and then now I want to solve for the field or for the potential, which always means that you have to solve a differential equation. Nature is just kind of picky like that. Now, I don't want to make this course into differential equations, and we try to stay away from it as far away as possible. But just remember that it still is a differential equation. It just looks a little different. There are, of course, Fourier transforms that will work in Minkowski spacetime, so you can easily invert it. But that's not really that's kind of moving beyond where I want to go. The other thing is that there is a shortcut. So in when we were doing when we were talking about the Maxwell stress tensor, we were able to calculate the force on charged objects and current carrying wires using the magnetic field and the electric field only. So that's kind of bypassing Maxwell's equations, and that means that you don't need to solve the differential equation per se, right? So there are sometimes shortcuts that you can make, but ultimately there will still be differential equations involved. That stress tensor is going to come back on Monday when we combine it with the pointing vector into the energy stress tensor, I think it's called. And that will be our crowning achievement. So that means today we have to talk about the actual Maxwell equation. So we had already the potential formulation, but that was limited to the Lorentz gauge. So now we need to actually take the steps and put that together. So we will find that there's a field tensor that you can use to describe Maxwell's equations, and then you get that field tensor. The divergence of that will be your source term, and then there's this anti-symmetric combination that shows you gives you the divergenceless part of the magnetic field, and it gives you the Faraday law, the two homogeneous Maxwell's equations. So then we'll have it combined into one object. This is going to be a little bit trickier because that field tensor just looks a little tricky. It's a 4x4 matrix, and because it's a field tensor, that means it's got two indices, which means that if you want to transform it from one coordinate system to another, you have to do linear algebra with two more 4x4 matrices. So it becomes a little bit tricky, but it's all there. But then we will, hopefully at the end today, we will be able to get back and show you how how we can find the electric and magnetic fields of a moving charge. I alluded to this when we were doing this using the retarded Green's function. So it's actually easier to do in relativistic E&M than trying to solve that or directly integrate that Green's function. And that is because it's just a length contraction effect, and I made that point. So I'll show you that it's rather straightforward to get the electric and the magnetic fields once you know how they transform under Lorentz transform. So you just start with an object that is stationary, so you have a frame of reference that is co-moving with that charged object, and then you find the field, and of course there's no magnetic field because it's stationary, so you just have a radially outward electric field, and then you just do a Lorentz transform on that thing, and then boom, 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 you get the exact same electric and magnetic fields as you would if you had done it the hard way with the retarded Green's functions. So hopefully things will start to click in place, and then that should be the end of today. The field tensor. Oops, tensor. All right, so we are on our way to put this tensor together. But let's. Why is this not removing? There we go. Let's see what it is we're trying to do. So we have the two inhomogeneous Maxwell's equations, same ones that we had before, Gauss. And of course, Ampere Maxwell. So that was, and again, we're taking c is equal to 1. We want to try to combine these two into a single expression because we already know that we can combine this one and that one as they are two parts of that J mu for current. So that would be rho and J. So it makes sense to try to see if we can find a way to get these two equations to show up as two parts of one equation. So we have some bookkeeping to do. So let's say we have on the right hand side we have a 4 pi rho, right, which is going to be 4 pi rho. Now rho, of course, is 4 pi j, so that would be rho, and it'd be jx, jy, and jz. We just need to kind of figure out how to get that from an object that we have a differential operator act on. So let's say here we're going to put the del t. Here we're going to put the del x, del y, and the del z. So we're going to make this into a 4 by 4. Okay, so and let's just see how we end up. So for instance, we have only one equation with rho, and that's of course Gauss's law. So Gauss's law says that the divergence of E is 4 pi rho. So that divergence of E, if you write it out, is of course it's del x, so written in this form, sloppy form, because I'm not paying attention to covariant contravariant, but that's how we'd write it in just basic index notation. So that means we need an EX here, because that's going to be picked up by so that's this one, and EY and an EZ, such that when we have that Nabla operator acting on it, the gradient operator or the del operator acting on it, this first row is going to give us Gauss's law. All right, now let's look at the next one. So if we have we have the current here, that that current J is going to have two contributions, one from E and one from B. Now the part from E is going to give you it's just the partial derivative with respect to time is going to give you J, which means that the x component of E is going to give you the x component of J once you take the time derivative and you put a minus sign in front of it. Okay, so that means that the time derivative here in this column is going to give you, so the x component is going to give you EX, but there's a minus EX. So here's a minus EX. And then the y component is a minus EY. And then there's a minus EZ. Okay, so that's the time component. Now we just need to fill out the that cross product. So so if you have the other part, so let's do that in purple. Okay, so we have still this one. So we know that is 4 pi j. Okay, or written out, that means jx is del b minus del b. Jy is del b, jz is del b. Okay, so this is x, y, yx. Okay, this is z, x, z. And this would be y, z, y. Okay, so that means that the x component in the y partial column is going to have an entry called bz. So that's going to be bz. And the z component is going to be minus by. Okay, so that's the first row. And then there's a 0 here. That's interesting. And then the second row, so this one goes here, right? So, or actually it's the third row because we're counting time as 1. So jy, so the z partial, which is the last column, is going to be bx. And the first one is going to be minus bz. And then this is 0. Okay. And then the last one, this is going to be dx by. And this is going to be dy bx with a minus. And this is 0. All right. So now we have all the right components. We just kind of need to decide how we're going to enumerate this. So so traditionally, actually, let me not get ahead of myself. The first thing to note is that this thing is actually asymmetric, and it's got no trace. You see that all the diagonal elements are 0, and it's asymmetric. What I mean, sorry, it's anti-symmetric, because asymmetric is something different. You see that if we take the transpose of this matrix, you see that all the signs, they all change, right? So see, they all change when we take the mirror in 1. Now, this is where our linear algebra is starting to fail us a little bit, because we need to actually start to write this as an equation that looks like this. So some kind of a partial acting on this field tensor, which we're going to call f. And it's going to give you 4 pi times j mu. Now the way we usually write this is as follows. So mu. So the and then there's a minus here. Now, there's really no good way to map this onto a linear algebra problem, because this is not an actual matrix. You can't multiply this thing on the right, on the left with a del operator. That just looks weird. What you really want to do is actually put the del operator on the right, but then you can't actually do that. Have the partial acting on it, because then it's on the right side of the thing that it's acting on. So that doesn't really work very well. But what we have here, therefore, is this is f. It's the field tensor. This we're going to call the field tensor mu nu. Let me see if that works. Yes, it's the field tensor. And I have one minus sign here. I just want to make sure I have it really right. Yeah, I think this actually, the way I wrote it is actually mu, not mu nu, but nu mu. All right, because otherwise you don't get the minus sign here. So for instance, you could also write this as del nu mu, and then you have you have it the way we wrote the tensor. Okay, so if you want to do it that way, then you would have the del nu here, del nu, acting on the tensor that is nu mu. So this then would be the nu counter, and this would be the mu counter. Anyway, so so it does work, but we are limited in our ways to translate this thing to tensors. But it does work. So this is what we get for this, for Maxwell. So this is now Ampere, Maxwell, Gauss. Ampere, Maxwell, Gauss. But now no longer involving the potentials, and also no longer limited to our to the Lorentz gauge. Okay, so now your assignment is going to be the following: using Ampere, Maxwell, Gauss, plus the anti-symmetry of F mu nu, show that, oops, come on. So this problem is not too hard. So first, you swap the two differentials. So this is mixed partials that you're allowed to do. And here you use the anti-symmetry. And now you see that this expression is the same as this expression, except that we have renamed our indices, right? So if you look, there's a nu here and a mu, where on the other side there's a nu and a mu. So because this is like, you know, a is equal to minus a, therefore this is 0. You know, write that. Okay, what about Faraday's law and Gauss's law for magnetism? Okay, so we had the divergence of E 4 pi rho, and the curl of B minus d dt of E being equal to 4 pi j. And these two together gave us that del nu mu is minus 4 pi j mu. Now the two that we want to add here are this one, and of course ddt of B is 0. So look very carefully here what's happening. The reason I wrote them under each other is to show you how closely related they are. So we have here, if we go from E to B, then that equation becomes a 0. And if we go from, from E to B here, we have to pick up a minus sign. And when we go from B to E, we can keep the same sign. Okay, so if we go from E to minus B, and from B to E, then we get the same equations that we have already solved, except now on the right-hand side there is there's a 0. Actually, let's use the convention of the book. So we're changing E with a B and a B, then afterwards with a minus E. Then the equations are the same. So we could redo the entire calculation, but now come up with a new field tensor that we're not going to call F, but we're going to call the dual of F. So we're going to call that F star mu nu, and then that would be 0. So that's one way. That's one way to codify to codify those other two equations. I don't think it is super useful because it's not to me immediately obvious what the dual of that field tensor is, because you have to really look at the elements in order to make sense of it. So there's another way to do it. So let's walk through that. So we have the okay, so this is now both Gauss's law for magnetism and Faraday's law. Okay, they're encoded in there. Now let's write out what we want to do. So first, we want to write down that the divergence of B is 0. All right, so that's del x bx plus del y by plus del z bz is equal to 0. Now, that's Gauss's law for magnetism. So let's see if we want to use the field tensor. Let's see where the bx, by, and bz are residing in our tensor. So bx would be in column 3, row 2. Okay, so that would be del x f column 3, row 2. I think we're going to do it like this. And then del y by is sitting on column 1, row 3. Okay, so that's del y, column 1, row 3. I think I swapped my 3 and 2. Yeah, plus del z, and then we need a bz. Bz is column 2, row 1. Column 2, row 1. Now, this is, of course, del 1. And this is del 2. And this is del 3. And those added together get you 0. So you see that it's this cyclic permutation of these 3 indices. So we could write this as del, let's say del A B, del A F B C, where we rotate those 3. So that sort of works, right? We could use the field tensor to describe this if we use these indices. Now let's look at the next one. So we have del T bx plus del y e z minus del z e y is equal to 0. Okay, now del T bx, that would be del T would be del 0, and bx, okay, where's bx? Bx is 3, 2. So that's f 3, 2 plus del y. Now del y is del 2. Okay, easy. Where's easy? Easy is 3, 1. That's f 3, 1 plus, oh, sorry, minus del. Now z is del 3 f ey 2, 0. I feel like I'm missing one. Hang on a second. Yep, fix it. Okay, so it's again, it's a combination of the same three numbers. So we have a 0, 3, and a 2, and we just have 2, 3, 0, and a 3, 2, and 0. But the signs are a little weird. We could keep going, but we would end up with the following. We would end up with the fact that in order to fix all the signs, we need to take, instead of taking the covariant del operator, we need a contravariant, and we would always get a sum of three terms, which makes sense, right? Because we have a ddt of something and then cross product. So we always have a sum of three terms, and all of those will involve elements of that field tensor. So we would have this one, del mu f nu lambda del nu f lambda mu is equal to 0. And then we have lambda mu nu being equal to, okay, here we go. So it's either 1, 2, and 3, or 0, 3, and 2, or 3, 0, 1, or 2, 1, 0. Okay, 1, 2, 3 was Gauss's law for magnetism, and these three will get you the three components for Faraday's law. Okay, so if you look at that, then this is the other two Maxwell's equations. It's not as satisfying as the other one, but it is what it is. By the way, these are the only 4 triples of numbers for which this expression is non-trivial, because of the anti-symmetry of the field tensor. It doesn't really make much sense to have anything other than these 3 combinations, 4 combinations. Okay. Now, so now from potential to field. So we have a we have this we have these two relations already that we have to unify. So before we had, we can always get the magnetic field by taking the curl of A, and we can get the electric field by taking minus the gradient of phi and d dt of a vector. So that's how we can go from the potentials to the fields. And so far we have talked about the current for vector. We've talked about the potential for vector and the field tensor. And we have a couple of relations between them. So we have the to go from the field tensor to the current. is a differential equation that says that del nu f mu nu is minus 4 pi j u. We can go from here to there by taking del nu a mu equals, actually, let me do that in different colors and let me give me more space. So that's the one we did last week. A mu is 4 pi j mu. But we haven't completed this particular step. The other thing that I should note is that this is only in the Lorentz gauge. Okay, remember that. So we kind of know our way around this this triangle, but we just have this this one thing that's missing. Now, if you look at this relation to go from the field tensor, sorry, from the potential vector to the field tensor, it seems to involve some kind of a differential operator, right? So you can take, go this way, use something, some del mu, maybe, or a del nu or whatever, and then we would end up with the field tensor here. So that's the general shape that we would need in order to get this going. So if we were to say, okay, let's say we have, let's say, the del mu a nu, and we're going to call that the field tensor. That would be a decent guess, but it's not complete yet. This is the point where you just have to take my word for it. So actually, it is del nu a mu. It's this anti-symmetric combination of the gradient of the 4 potential that gives you the field tensor. So now we have, we can go this way. We just say f mu nu is del mu a nu minus del mu a mu. The beauty of this notation is also that now it's immediately obvious that f mu nu is anti-symmetric in the indices, right? Because you just swap those two terms, the del a terms, by swapping the indices, and then you pick up a minus sign. So that's the nice thing about writing it this way, but it is quite a lot of work to actually get here if you want to do this from first principles from the tensor. From the field tensor. But what we can do is we can actually verify that the following. So this is another assignment for you. So show that this choice for f mu nu in terms of a mu's gives you del nu a mu is j, oops, 4 pi j mu in the Lorentz gauge. All right. So so we want to calculate the Yeah, okay. So we know that del F mu nu is 4 pi with a minus j mu. But now we also know that F mu nu is actually del mu a nu minus del mu a mu. So if we write this out, we get del mu a mu a. Oops, sorry. I got so excited. Del mu a mu minus del mu a mu. This one, the first term, you can swap. I'm being very verbose here. You can swap the partials because you're allowed to do that. A mu. The second one is already the Lambertian, so I'm going to leave that alone. This one is 0 because that is the Lorentz gauge. The Lorentz gauge. Okay, so now we have on the left-hand side we have rewritten the del nu F mu nu to this expression, which ends up being minus the D'Alembertian of a mu, which is minus 4 pi j mu. Okay, so putting everything together, we get what we were supposed to. We get del nu, a mu is 4 pi j mu. Done. Now let's actually apply this thing. The field of a moving charge. I started too low. The field of a moving charge. Now we have the field tensor, and we know that because we wrote it like this, we know that in some other kind of frame, we would have to take the Lorentz transform twice. So mu, alpha, nu, beta, and start out with this in the untransformed frame. But like I said, it becomes a little tedious to write it down this way. So so I'm just going to give you the shorthand versions of this transform. So if you have a so v is in the x direction, then this is how the fields transform. Your E x is unchanged. Your EY is going to be gamma EY minus VBZ. And remember, this is in the CGS system, the E and the B, you can just put them together. But this one is unitless because that's V and normalized by C, so the units are fine. So EZ prime is gamma, the original EZ minus VBY. Okay, so that's the electric field. Now the magnetic field, X is unaffected. Y is going to be gamma BY minus VBZ. z, and oops, b z prime gamma b z minus v e y. Okay, so the fields are the fields are being mixed as expected. So let's say we have this we have some kind of a charged object and some q, and in the K frame, which is co-moving, it's stationary, and in that case, the only field that we have is the electric field. So the electric field is we can just write it as usual. It's q r vector over r cubed, or q r unit vector over r squared. All right. So what does that mean? Well, that means that we can write our EX as follows. EX is, and of course, we're putting the origin at the location of that charge, okay? So EX is therefore the x times q over r cubed, and EY is, oops, is of course y times q over r cubed, and b is 0. All right, so let's transform this thing in the lab frame. Okay, prime frame, lab frame. All right. We get the x prime is it's unaffected, but we need to change our coordinate system, because right now we're still in the unprimed coordinate system. So even though that EX is the same, it's described in terms of the unprimed coordinates. So X is gamma X prime. Okay, and who? And gamma X prime, and then the length here is going to be gamma squared X prime squared plus Y prime squared, because that's what the length is. 3, 2. Yep. And now EY is going to be gamma times EY. But EY was actually not going to be transformed. Oh, sorry, was going to be transformed with the gamma. Okay, but it is gamma times now EY. Now EY itself was Q times Y prime, and then still the same denominator, X prime squared plus Y prime squared. Okay, let me make sure that I didn't mess this up. So yeah, we had a Y times Q and Y prime was Y, because we don't have length contraction in the Y direction, because it's only the because it's moving in the X direction. So that's why we're able to change that Y to a Y prime, and all we need is a all we need is we need this. Okay. So this is identical. We're not doing z because y and z would be identical, right? Because there's rotational symmetry around the x-axis. The interesting thing to see here is that actually it is radial, this field. So this field is radial. But it's definitely compressed, right? So as we were discussing a couple of weeks ago, the electric field lines are kind of hunched together, and then they kind of spread out in the frame that is the lab frame. So this is still moving like this. So so hopefully you agree with me that just taking this Lorentz transform on the field of a stationary charge is easier than finding the field by integrating that monster green function. It's also, I think it makes physically more sense because really that is what is actually happening. Length is actually being contracted, which is why those field lines get so scrunched up. And I'm not going to do B, but B follows in a very straightforward manner. All right. Well, ladies and gentlemen, we did it. That was motivation number 2 for finding the relativistic description of electromagnetism. I hope you appreciated the ride. Also understand why it's important to do it this way. And that means that we have just one more class, and then we'll deal with the Maxwell stress tensor, and we'll add the pointing vector to it. It's going to be a lot of fun. All right. If you have questions, just hang around for office hours as per usual. Otherwise, I will see you next week.